All right, guys, in chapter 3, we're going to start off by really reviewing stuff from Algebra 1. This is a lesson that is on the properties of linear functions in linear models. So hopefully this is making very good sense to you. I'm going to kind of cruise through and remind you about lines and how they work. So the objectives for today, we're going to graph linear functions. We're going to use the average rate of change, another name for slope, to identify linear functions. We're going to determine whether a linear function is increasing, decreasing, or constant, and then we're going to build linear models from verbal descriptions. So those are the objectives for today. We have 4 of them. Let's get right into it. So first one, graphing a line. This should look very familiar to you. A linear function can be put into the form y equals mx plus b. Here we see that we've replaced y with f of x. It just is function notation. So another name for f of x is y, right? The graph of a linear function is a line with slope m. So m represents our slope. And b is the y-intercept. Okay, so if I have something like, and then it says functions that are not linear are said to be nonlinear. So if I have something like y is equal to 2x minus 3 or something like this, you should be able to identify 2 is the slope, so m is equal to 2, and then b, the y-intercept, is equal to negative 3. So how I would go about graphing this, one way to go about graphing this is you can, like, what I like to do if I have a line that is in this form is I like to start with my y-intercept. So at negative 3, okay, I know that this thing crosses. And the reason that we know this is because at this particular place, this is the y value, this is the x value, x is equal to 0. When you set x to equal 0, notice that this whole term goes away and you're just left with b. That's why we will always have a y-intercept of b, the constant term that is outside of the variable. So we have negative 3. Okay, and then the slope is 2. Slope, just to review, slope is equal to the change in y over the change in x. All right, so if I have a slope of 2, that means the change in y is 2 over a change in x of 1. That means is, in the y direction, I'm going to go, this is positive here, positive 2. So I'm going to go up 2 over 1, up 2 over 1. And I'm going to have this line. I can also go down 2, back 1. So I have this line that looks something like this that goes through negative 3 and has a slope of 2. There's other ways that you could graph this. You could also just plug in points for x. So if, say we want to know what happens to y when x is 5, you can plug a 5 in. So if I plug a 5 in there, I could say, okay, 2 times 5 is 10. 10 minus 3 is 7. So I know that at 5, I am all the way up at 7, right? So I can get that other point on the line. So that's a linear function. Hopefully that is very familiar to you. Example 1 says, let's graph y equals, or f of x is equal to negative 3x plus 7. And then it says, what are the domain and the range? So using the strategy that I just shared with you, and that should be very familiar, we can go up to 7. We can put a point, and, because that's where we know it crosses the y, right? This is y, this is x. Okay, then we know that the slope is negative 3. So from this location, the line's going to be going down. So I'm going to go down 3, 1, 2, 3, over 1. So 1, 2, 3, over 1 puts me there, and then 1, 2, 3 again, and over 1 puts me somewhere in there. And I get this line that looks like this. All right, again, with everything that we graph, you guys, you can always make an XY table to see what happens. So I could be plugging in, you know, negative 2, negative 1, 0, 1, 2, choose values to plug in. And then when we plug these things in, negative 2, so if I plug that into the function for x, right, this is my x values, and I chose them because x is independent, I can plug it in here. Negative 3 times negative 2 is 6. 6 plus 7 is 13, I believe. So at -2, I'm way up at 13, so this thing does grow pretty steep, somewhere up in there. And then at -1, we would plug the -1 in, right? So hopefully, again, this is just review. You'd get 10 there, and then at 0, you'd be at 7. That's our y-intercept. And then at 1, we're at 4, and then at 2, we're at 1. Okay, so 2, 1, looks like we already have a point there. At 1, 4, we have a point there. That's how another way that you could graph this, by plugging in points. All right, so I'm giving you some strategies there. This just walks us through the solution. So now we're going to move on to objective 2. That was objective 1, how do we graph a line? Objective 2, now we're going to use the average rate of change to identify a linear function. So again, average rate of change of a function is slope. So how much is it changing in the y direction versus the x? It's the change in y over the change in x. Okay, so here it says we have a strain of E. coli, and it's put in a petri dish 30 degrees Celsius, and it's allowed to grow. The data collected is shown below. The population is measured in grams and the time in hours. Okay, so you might get one like this where they give you guys a chart. Hopefully they help you identify that, yeah, this is x, this is y. So notice we just, from the chart, they've created these nice coordinates for us. We can go ahead and look at those coordinates and determine what the slope is between each time frame. All right, so really we want to know what is the average rate of change over time. If it's linear, it stays constant. All right, so each time I find the slope between these two things, it should stay the same. If it doesn't, if it's increasing or decreasing, then I know that I'm not dealing with a line anymore. So let's see what happens here when I do this. Again, the y values are second, right? So the change in y would be 0.12 minus 0.09 over 1 minus 0. Okay, so I just took this, subtracted this, took this, subtracted this. That's how you find slope. You divide them out. Okay, so 0.12 minus 0.09 would give us 0.03. 0.03 divided by 1 would just give us 0.03. Okay, so what I'm going to have for my first slope is 0.03. What I want to see is, does that change when I go to my next time frame? So for the next one, I would do 0.16 minus 0.12. That's the change in y over the change in x, 2 over 2 minus 1. So when I get this, it's 0.04 now over 1. All right, so clearly the rate of change is different between the different time frames. Otherwise, I'd be getting the same number every time. And if I keep going here, it looks like the next one would be something like 0.06, and then it would be 0.07, it looks like, and then let's see, what's the last one? 0.1 or something like that. Okay, so the rate of change is definitely increasing over time, and if that happens, you will get a graph that looks something like this. This is more of an exponential type of graph, but really for this purposes of this lesson, they're just going to want you to identify, is this linear or not? And the reason that this is not linear is because the slope is not staying constant, it is changing. The red here, these are all our slopes between the various time frames. We can get an average, so don't be confused, you guys. You can get an average slope by taking 0 and 5 and looking at these numbers and subtracting them out. You can get some kind of average slope, but they're asking you to identify, is the slope constant over time? So you need to do a bunch of the slope calculations and see if they're coming out the same over the same time frame. All right, so this just goes through getting those answers that we just got, right? Then here's the explanation. Because the average rate of change is not constant, the function is not linear, as we talked about. Okay, so objective 3, moving right along. Oh, and somehow let me do this. So objective 3 here, determine whether a linear function is increasing, decreasing, or constant. Okay, so let me just show you guys what that means. If something is if a linear function is increasing, what that means is from left to right, it's going up. Okay, so this is increasing. All right, if you wanted to see a decreasing function, that would be from left to right, it's going down. And this is called decreasing. And if a slope is not changing at all over time, I shouldn't say slope. If something has no slope, right, or if it has an undefined slope, let me show you a picture of that. Okay, no slope looks like this, where it's just a flat line. This is constant. All right, the other constant that you might see is this guy. All right, this particular constant is when we have zero slope. So the slope is 0 here. When you have a vertical line, notice that doesn't pass the vertical line test, that is undefined. Because what you'll see happen there is the change in x is 0. And so if you have the change in y over the change in x, and change in x is 0, what that means is I'm going to divide by 0. I'm going to get something here like, I don't know, it could be 10. Change in y could be anything. Divide by 0. Anytime you divide by 0, it's undefined. All right, so the two different constant functions are those guys in blue. All right, so let's just cruise through. And algebraically, you guys, algebraically what's happening is that here, for decreasing, slope is negative. All right, for increasing, slope is positive. All right, for this one, slope is 0. For this one, slope is undefined. Okay, so then they're going to go through and teach you all those. So here it says determine whether the functions are increasing, decreasing, or constant. All right, so you should be able to look at something here and very quickly tell me if this is increasing, decreasing, or constant. Here, the slope is positive. It's increasing. Okay, if the slope is positive, we have increasing. Here we have a negative slope, therefore it is decreasing. If you were to graph these functions, this would be going down, this one would be going up. All right, so, and then they want the domain and the range probably, which we haven't really talked about, but domain and range, you guys, for these, if it is a linear function, domain and range will always be all reals. The reason for that is you can plug anything you want in for x and you will get a y value out. So these lines go on to infinity. So you notice they're in interval notation there. The domain is negative infinity to infinity. Same with the range, right? If we have an increasing or decreasing function. If it's a constant function, that's the only one where we have to be careful with our domain and range. All right, so objective 4 now, we're going to build linear models from verbal descriptions. Okay, so modeling with a linear function. If the average rate of change of a function is constant, m, a linear function can be used to model the relation between two variables as follows. Y equals mx plus b, where b is the value of f at 0. That is, b is equal to f of 0. That just means when I plug a 0 in for x, okay, so notice, if I have, let's go back to a previous example. If I have something like 2x plus 3, okay, and I make an xy table, and I plug a 0 in for x, okay, plug it in here. 2 times 0, whatever that is there, will always go away, right? It'll just become 0, and I'm left with this. So it's saying that b is the value when x is 0. That's all it's saying. All right, so let's get into example 4, and then I think we have an example 5 possibly, or do we? Yes, a couple of examples related to these that we can use in the real world, and we do use these quite often. You will see here some business applications. So, straight line depreciation. Basically, I don't want you to have to read this whole thing, but basically, you guys, some companies straight line depreciate. Basically, they say, okay, if we buy a truck, then we think that truck is going to last us 7 years because, you know, that's what they're forecasted to last us. We can depreciate the value of that truck over time so that on our asset books, this is an accounting thing, on our books, we can decrease the value of our asset every year by a certain amount. This is a straight line depreciation. Depreciation actually doesn't work this way, but if you look at a big picture, it works just fine. Okay, so let's go ahead and do that. For this problem, we are going to take $35,000 truck and we're going to depreciate it over 7 years. So over 7 years period, the value of the truck is going to go from $35,000 down to 0. Okay, that's a Y value. All right, that's the Y value. So 35,000 minus 0 over 7, okay, because it's over 7 years, just leaves me with 35,000 over 7, which comes out to, as they've posted here, $5,000 per year. So the truck is going to lose value on their books at $5,000 a year. Now in real life, it loses way more value the first couple of years, and then that begins to balance out. And eventually, over time, if you take really good care of your cars, it can actually go back up in value. You know, if you're trying to get something like a 1960 Ford Mustang, for instance, and somebody has kept it in immaculate condition, you're probably going to pay more for it than they did in today's value. So it can eventually go back up if you take good care of your vehicles, but for the most part, people just are not collecting cars to resell them like that. They're collecting them, or they're just buying a car to get a job done or get to point A to point B. Anyway, that is an example of straight line depreciation. Oh, they want you to graph it. What's the book value after 4 years? Interpret the slope. Okay, so if we're to graph this, the slope is 5,000, right? So what that looks like is at year 0, we're at 35,000. Okay, so when you go to graph this, we'll call this 35K. Okay, year 0, we're here, and then we go to year 1. At year 1, we've dropped value by 5,000. Okay, so now if we're going by 5,000s here, if this is 30K, now we're here. Okay, and then 25, 20, I didn't have enough room here, but anyway, this thing will end up being a line, right, that's going down over time. So the graph would look something like that. It says, what is the book value of each truck after 4 years? Okay, so after 4 years, it's going to drop. Okay, that's going to be an X value that is equal to 4. So if I use my equation, which by the way we haven't really talked about an equation, but the equation for this, we know the slope is 5,000 and it's going down. So the equation would be this: y is equal to negative 5,000 because it's going down in value 5,000. X, okay, plus 35,000. Starts at 35,000, and it's going down by 5,000 every year. So if you plug a 4 into this, notice what happens. 4 times negative 5,000 is negative 20,000. So if we subtract 20,000 from this, we have a truck value that has 15,000. So after 4 years, it's worth 15,000 on the books. The slope is just how much it is going down in value per year. That's what the slope means, and that's what interpreting the slope means. And then it says, when will the book value of each truck be 10,000? Well, after 4 years, if it's 15,000, it's going down by 5,000 a year. Then I could say after 5 years, just knowing that. Or I can say, okay, let's replace our y, which is the value of the truck, right, with 10,000. So 10,000 is equal to negative 5,000, x plus 35,000. And you could solve this for x, and you will end up getting 5. All right, so you can go ahead and do that, but I'm not going to take the time to do it here. This shows you all of that work, right? And then the very last thing we're going to get into here, guys, I know this is a very long lesson, is example 5, supply and demand. So supply and demand functions can also be linear. And you know what, I'm actually not going to take your time to do all this, but basically with supply and demand, they're going to give you a supply equation, which is usually S of P, and a demand equation, D of P. And they're going to have you guys figure out what the equilibrium is between the two. So that's the only thing that's really new about this problem. To figure out a a equilibrium, that's just where are the two equations the exact same. So what I do is I take the two equations. All right, here are the two equations that were given. One's S of P, the other is D of P. Okay, supply and demand. They want to know where are they the same? Where's equilibrium happen? So set them to equal each other and then solve for P, which is what they do here. And you get P is equal to 100. All right, so at $100 a cell phone, no one's making any money. That's equilibrium. So they want to probably charge more than that, right, in order to get, and then you can plug that back in and figure out at how many phones that happens. So for them to be making money, they're either going to want to increase their price or increase their sales, one or the other. Okay. So then they have you go through that and graph these and see where the place meets, right, where the two lines meet. And that's pretty much it. So I'm going to let you guys go there, and we'll see you guys.